Hi, good morning. So if you are already joining the live stream, please let me know. I have given you so far about 7 weeks of lectures and also some tutorials and assignments. I think that generally the feeling I get is that many of you are following the lectures. And if you have questions on a live session like this, that would also help me to understand specific problems or any inputs that I have to have for more lecture notes and so on. Okay, please let me know. I'm waiting. Okay. Okay, so let me, yeah. Till now, if you go back and look at what you have studied, we have looked at quantum chemistry and the model problems. The next 3 weeks, we shall look at what is the important part for chemistry, namely the chemical bonding aspects. Quantum chemistry that we have learned so far is essentially the basic aspects of quantum mechanics and the model problems. But the problem of chemistry is the problem of understanding why molecules form, why molecules are unstable and why they react, and when they react, how they transform themselves into various other species, typically a chemical reaction. Therefore, it is important to have applications of these mechanical tools, the quantum mechanics tools, as I'm saying, directly to understand the electron interaction problem. In chemistry, it is the valence electrons which are most important for the bulk of molecular behavior and bulk of the transformation properties. Core electrons do help, core electrons do contribute, but valence electrons are the most important species for the reactivity of any compound, or for that matter, any metal or any element. Therefore, the electron problem has to be studied, and the electron problem has to be studied along with the assignment of the electron energies using the 3 quantum numbers that you have already seen: the principal quantum number n, the angular momentum quantum number L, and its projection m. The 4th quantum number of the spin of the electron is also needed in order to understand the electronic configuration of the atoms. And whatever you find in the tables of inorganic chemistry and physical chemistry textbooks regarding the electronic configuration of the atoms from hydrogen all the way to uranium, The configuration is an approximate classification. In principle, there is no s orbital. I mean, in a real sense, there is no s orbital or p orbital for any element other than hydrogen, which has more than one electron. It is an approximate starting point. It is reasonably good and reasonably accurate starting point that we think that atoms have s orbitals, p orbitals, d orbitals, and so on. No, these are all our description of the probabilities of finding the electrons in around various locations about the atom. And these are important starting points for understanding what we call as the formation of a molecule. So until you provide specific questions or things, I would explain what is likely to come in the next 3-4 weeks. The first and the most important thing is, what is chemical bonding? What is the quantum mechanical description of a chemical bond? The Nature of Chemical Bond is a very famous book written by Linus Pauling many years ago. Yeah, so let me, for those of you who haven't seen it, this is an extremely important book. And it gives you a very beautiful account of the preliminary, or what are called early methods into the description of a chemical bond. Let me see if there is if there are any specific, yeah, okay, so this is fine. I think we can continue on. Okay. Yeah, the nature of chemical bond, we'll leave it here. So, bonding, chemical bonding, is essentially the result of the interactions between electrons of the atoms involved in bonding, and a very beautiful way of simplifying the electron interactions from the nuclear motion was first provided by Born and Oppenheimer. And you have seen my lecture notes on the Born-Oppenheimer approximation, which separates the nuclear component from the electronic component, while at the same time retaining the effect of the electronic components and the electronic energies in describing the nuclear motion through the potential energy surface. That is the result. Okay. This separation helps us to basically divide the molecular problem into two components. For example, if we talk about the simplest stable molecular species, ionic species, is the H2+. This is the one electron molecule. While it captures some basic ideas about what is called the linear combination of atomic orbitals of two hydrogen atoms to form a molecular orbital, and to form what is called an anti-bonding orbital, a bonding and anti-bonding orbital pair, and how the electron can be stabilized by its location in the bonding orbital and so on. An important aspect that this misses out is the one that is present in every other molecule that you can think of, namely the electron-electron correlation. This is the most important unsolved problem in all of chemistry. And every method that we have so far come across is unable to solve this except in an approximate way, and then provide a certain approximate or even what you call an empirical way of describing parts of the electron-electron correlation. It can be empirical, it can be even mathematically clearly defined and so on, but the point is it is still an approximate way. We do not know how to solve this problem exactly. Exact solution not available yet. Hydrogen molecule is the first example where the electron correlation problem appears as the interaction between the two electrons in the two hydrogen atoms. Okay. Another thing that you would notice is that in solving quantum mechanical problems, we always start with a fixed frame where we talk about a particle, we talk about the interactions between the particles, either coulombically or by any other means. And then when you solve the Schrodinger equation, you think that things are different and the particle character is lost, and you talk about the electron densities. This is common in all of the theoretical methods. Okay? Let me see if there are anybody who has while I go on, I also want to answer any specific questions that some of you might have. Okay, whoever is there is only listening. Oh, there is a question. Yes, okay. So here is the first one. The question is from one Prashanta Das. Can you give a summarized way to define atomic orbitals, particularly D and F, from radial and angular component given in the lecture note? Okay. D and F are the radial and angular part. Okay, let me summarize it. So we will continue this discussion after that question is answered. Okay. So let me start with the D orbitals. Okay. Now, the solution to the Schrodinger equation gives you specific requirements for the three principal quantum numbers, and the D orbitals correspond to the angular momentum quantum number L having a value 2, and the M having any one of these values, 0, plus minus 1, plus minus 2. N, by the requirement of L being 2, N has to be a minimum of 3, because the maximum value of L is N minus 1. Is N minus 1. Actually, it is N minus 1, and then it is N minus 2, down to 0. Okay? So if you talk about D orbitals enter the picture only when we have a principal quantum number N equal to 3 and L equal to 2. Therefore, we have 3D. And then the spherical harmonics, Y2 plus minus 2, Y2 plus minus 1, Y2, 0, 5 functions represent the 5 D orbital functions. Please remember, these are complex functions. These 4 of them are complex functions. Okay? Therefore, we cannot have a pictorial way, but these 5 functions will always be there, whether it is N equal to 3, or whether it is N equal to 4, or N equal to 5, and so on. So there will always be 5 D orbitals as long as the principal quantum number is greater than or equal to 3, and the 5 D orbitals with the electron spin requirement and the Pauli's antisymmetry principle, which I'm going to describe in the next week's lecture, ensure that no more than 10 electrons can occupy these d orbitals. Okay? This is true for all the 5 d orbitals. Now, if you look at the nature of these d orbital functions, you can see that y22 plus minus 2 contains a sine square theta and an exponential plus or minus 2i5. Okay. And the y21 plus or minus contains a minus or plus sine theta, cos theta, e to the plus or minus i5. And the y20 is 3 cos square theta minus 1. That's it. There is no exponential because the m is 0. Okay? So all these are, except this one, all the other 4 are complex functions. So when we talk about d orbitals, we have to either say 3d plus minus 2 or 3d plus minus 1 or 3d 0. But we are always used to a Cartesian representation, namely xyz coordinates, and we know that the origin of the coordinate system is at the nucleus, and these are the angles theta and phi are the polar angles of the electron position with respect to the origin on a sphere. Given all of that, you need to have a real representation that is an x, y, z representation. And therefore, what you do is you examine these functions, the 3D, for example. Let's start with the 3D, y20, this one, 3 cos square theta minus 1. Okay. So, leaving out to the length or the radius of the sphere in which the electron is likely to be found, I mean, assuming a constant sphere, 3 cos square theta minus 1 is nothing but 3z squared minus 1. Therefore, you can see that there is a dz square orbital, which is essentially d3z square minus essentially r square, but we have chosen the r to be 1. Yeah. Follow-up question. Yeah, no, but let me finish this question.
Same guy.
Let us see. Yeah. From these functions, yeah, I'm writing that. It's the same thing. Yeah, I'm explaining the same thing. Okay. So precisely that's what he was looking for, namely how to write this in terms of x, y, z. Okay? The question is on that. Therefore, 3 cos square theta minus 1 is essentially dz squared. Okay. Or it's 3d3z squared minus r squared, which is simplified to dz squared. On the other hand, if you look at the y2 plus minus 1, it is sine theta, cos theta, e to the plus minus I phi, which if I expand, sine theta, cos theta, you have cos phi plus minus I sine phi. Now, cos theta is z. Sine theta, cos phi is x. Sine theta sine phi is y. Therefore, y2 plus minus 1 is essentially z x plus or minus y. Okay? So it is zx plus or minus I zy. So what you have is in the y21 plus minus 1, you have a real part which is dxz and an imaginary part which is dyz. So the real part is a linear combination of y2 1 and y2 minus 1. If you take the negative combination, because y2 plus minus 1 is minus plus. So if you take the difference, you will get the real part. If you take the sum, you will get the imaginary part. So this is what we normally represent in our pictures, because pictorial representations mean that we are using real functions and in real space. So this is the connection between what you call as the xz orbital and yz orbital. Please remember, these are linear combinations of what are called degenerate orbitals. Therefore, they themselves are atomic orbitals as well. There is no reason that you have to explain a d orbital with an exponential IV. You can actually represent a d orbital with a real part, xz part, or the yz part. Therefore, this is what you find in the textbooks and also in my animations as the dxz and dyz orbital. Likewise, d, if you take the L equal to 2 plus minus m equal to plus minus 2, you get sine square theta. E to the I phi is cos 2 phi plus I sine 2 phi. So in polar angles, if you convert them, cos 2 phi is cos square phi minus sine square phi. And sine 2 phi is cos phi sine phi, barring the number 2. Okay. Now you can see that sine square theta cos square phi minus sine square theta sine square phi is the real part of y22. The real part here. The imaginary part of y22 is sine square theta cos phi sine phi. Therefore, you can see that this is sine square theta cos square phi is, is x square. Sine square theta sine square phi is y square. Therefore, this is the real part is a dx square minus y square. This is sine theta cos phi, sine theta sine phi. Therefore, this is dxy. So the real and imaginary parts of y22 give you the real and imaginary real representations in spatial Cartesian coordinates, dx square minus y square and dxy. Therefore, this is how the d orbitals are represented from the complex functions. The same thing you can do with the f orbital. In the f orbital, you will have to basically pick up all those things, cos 3 phi plus I sine 3 phi. And you expand this in terms of single angle formula, cos phi, sine phi, etc. And you substitute sine theta cos phi is x, sine theta sine phi is y, cos theta is z. You will get exactly real representations f, x, y, z, and various other things that you have found in my lecture notes. Therefore, the f orbital corresponds to the fact that L is 3. And therefore, f orbital cannot be there as a part of the atomic label unless L is 4. Okay, so that's important. Okay? 4 and above. Therefore, you have lanthanide and actinide series coming in the f orbital after S is 4s. Okay, so there is a third question. Okay, I hope I have answered the question on the functions, how we are getting dx, y, z, and dz squared. Then there's a question, sir, can you explain about HF HCl using MO theory? I would like to suggest you to wait because that's part of my lecture in the next 2 weeks. On the chemical bonding, because I think I have completed the hydrogen atom reasonably completely. The week 8 lecture and week 9 lecture will start looking at the chemical bonding, and there will be a formal lecture, so please wait until then. And then the other question I have this is from Yashwant Mailswamy. So please look for the lectures in the next 2 weeks. Okay? Vishal Thakur has a question of what is the significance of degeneracy with respect to non-degeneracy for orbitals? Okay, that's a good question. Yeah. Okay. Yeah, this is fine. I can go here. Yeah. Yeah. So degeneracy versus non-degeneracy. One is two things. If an orbital is non-degenerate, there is no issue. The orbital is unique and it has a certain energy. The electron occupies that orbital. The maximum number of electrons that can occupy that orbital is 2. Okay? Because any non-degenerate orbital. Example is all the s orbitals. They are non-degenerate. They can only have 2 electrons. A degenerate system orbital essentially means that there are multiple quantum states available for the occupancy for the same energy. In the case of p, of course, degeneracy means that there are 3 p orbitals, and therefore when you are assigning the electron coordinates and the electron quantum numbers, you have to ensure that since the 3 orbitals are equal in energy, the electron has a possibility of being in any one of these orbitals. Therefore, if you have 3 electrons that would occupy the p orbitals, the most likely possibility is that these 3 electrons will occupy the 3 p orbitals. One way to look at it is that the electrons have Coulombic interactions, and therefore they repel each other, and therefore they try to be as far away from each other as possible. Therefore, the 3 p orbital orientations give them reasonable spatial, reasonable space, I would say, to be away from each other. And also, the moment you have a degenerate orbital, the most important part is, suppose you have px, py, and pz. So the psi1 is px, psi2 is py, psi3 is pz. But then, you know, the very fact that these orbitals have the same energy also tells you that the electron wave function is not limited to only these 3 choices, but any linear combination. For example, if I write a psi and write A psi1 plus B psi2 plus C psi3, if I write the psi, recall that with respect to the Hamiltonian on psi, this psi is equally acceptable because Hamiltonian on A psi1 plus B psi2 plus C psi3 will give you the corresponding energy. Since all 3 are degenerate, the energy E is common, and therefore you will get A psi1 plus B psi2 plus C psi3. Okay? Therefore, the linear combination of all the degenerate orbital is also an equally acceptable and equally important solution to the electron probability problem as the individual solutions are. In fact, you cannot say which one is individual, which one is linear combination. We assign an axis system and we assign a px and py and pz orbital. But if the electron were to be there, it can be in any linear combination of these atomic orbitals. ABCs are arbitrary constants. And therefore, locating an electron to a px orbital or a py orbital or a pz orbital in the absence of other interactions is not correct. It cannot be done. It should not be done. Why we say the pz orbital, for example, when 2 atoms come together and there is a pz orbital and they form a bond, that's easier for you to explain because there is a polarization of the electron density towards the bond. Therefore, you call that as pz. And then you call the 2 orbitals which are perpendicular to that as the px or py. Okay? But left to itself, if the orbitals are of the same energy, then the electron can be in px or py or pz or in some linear combination. This is true only for the hydrogen atom. You take helium atom and others. Remember, the p orbitals are still degenerate, but the p orbitals are no longer having the same energy as the s orbital. Therefore, your degeneracy is limited to 3 instead of in the hydrogen atom, it is limited to n square terms, 4 or 9 or whatever. So it is possible for you to specify the orbitals x, y, z with some accuracy, but the electron occupying one electron occupying any of these p orbitals cannot be polarized or cannot be localized into x or y or z. It becomes localized only when there is another influence of another atom or another electron from some other source. Okay, so the pictorial representation of px, py, pz, remember, has its own limitation. Okay? So this is the difference between degeneracy and non-degeneracy. In the non-degenerate case, we don't have any problem. The electron occupies that orbital. Yeah, that's the same question that I answered. Okay, so, yeah, let me know if this is clear or if you need slightly different way of explaining. To me, it appears that this is the most important way of looking at the p and the d orbitals. The same thing with the d orbitals also. In the case of d orbitals, you have 5 orbital locations. See, in crystal field theory, you often use the 5 orbitals as though very distinct orbital. The reason for that is the ligands which come towards this metal crystal, the ligands basically influence the orientation of these electrons in the metal atom to specific d orbitals. If the ligands are not there, and if metal atom has 1 d electron, it can be in any one of these 5 d orbitals, or it can be in any spatial linear combination of these 5. Therefore, picturizing the electron position as corresponding to a dx squared minus y squared as the lowest energy or highest energy, it doesn't make sense. It's important only when there are other electrons which affect the position of the electron in that central atom. This is another thing with respect to inorganic complexes you should have in mind. So, okay, so these are the questions that have been asked so far. So let me go back while, if there is, yeah, there is one more. Yes. There's one more question from Sami, which says, so basic difference between bonding and non-bonding orbitals, degenerate and non-degenerate orbitals, in simple words. Please give me some time, because the bonding and anti-bonding orbitals are part of the lectures which are coming forward. So I'm glad that you are actually jumping ahead of what I have to say. But please wait until then, because the next week's lecture is on bonding orbitals and also the anti-bonding orbitals. In simple words anyway, I'll tell you what it is. I think about the degenerate orbitals I've told you. Yeah, let me see the bonding and anti-bonding. So let me just go to that. Yeah. See, the first example where you would see the bonding and anti-bonding orbital come up seriously is the hydrogen molecule. I'll say it in words. The hydrogen molecule, if you think about it, is a 1s electron here, 1s electron. They're both a ground state. Therefore, if you think about the 1s electron, the radial probability of the 1s electron for the hydrogen atom will have something to do with across all, or the electron probability will be this similar, and the radial probability, you know, it sort of decreases. And for the 1s electron, sorry, this is the radial function. Let me write down the radial probability. The radial probability for the electron is something like this, R. And this is the R square for the hydrogen atom. Therefore, the electron density as you go away from the nucleus center decreases. So if the electron density is also 0 at the nucleus. Therefore, if you plot the electron density is something like that. It's going to be that. Suppose there is another hydrogen atom here, which has its own electron. And the electron density for this hydrogen atom, you see, the electron density is, of course, proportional to R. So it is the same thing on this side also. There is no direction. Okay. But now you have the second electron here from the second hydrogen atom. This is hydrogen 1. This is hydrogen 2. Therefore, this has an electron density for its own hydrogen atom without any influence of this. It has it this way, and also it has on this side. Therefore, you see the electron densities overlap. The constructive overlap. If the psi 1s A, the wave function of the electron 1, and the wave function for the electron in atom 2, if they add, then the electron density between the two hydrogen atoms will be more positive than the electron density due to this electron alone, Because if you take the square of the psi 1s A and psi 1s B, and you take the absolute square, the integral, sorry. This will contain three terms. It will contain psi 1s A square. It will contain psi 1s B square. That is the electron densities of the individual electrons in the two atoms But it will also contain an additional term called the 2 psi 1s A, psi 1s B. Okay. So this is a positive influence. So in terms of simple language, it is like two waves, both of which are essentially adding their amplitude to give a larger wave. And therefore, the intensity of the larger wave, which is the square of the intensity, is more than the sum of the intensities of the individual waves. So the sum of the intensities of the individual electrons, if you think about it, is less than the two electrons being together. This is called the bonding influence. That is, the net electron density between the bonds of between the two hydrogen atoms is now more than if the two hydrogen atoms were away from each other. Since there is an increased electron density, this is almost equivalent to what the Lewis did as two dots that were placed between the two hydrogen atoms in the Lewis simple model of the electron dot theory, okay, octet model. He puts the two electrons between the two hydrogen atoms. Same thing here. We don't put the dots, but we put increased electron density in the modern language. Okay? So this is called the bonding influence. The anti-bonding influence is the opposite of it. If, for example, the waves cohere in a negative way, if one wave is coming like this, another wave is coming like this, but they are anti-phase to each other, when the two come together, the wave gets killed. Therefore, there is a reduced intensity or a depleted electron intensity between the two hydrogen atoms than if they were two independent hydrogen atoms. The depleted electron density essentially is against a natural state of the two hydrogen atoms forming a bond, because we know hydrogen molecule is stable. Therefore, the natural state is the bonding state. The depleted electron state tells you that the two hydrogen atom electrons density is less in the middle than it is elsewhere. This is what we call as the anti-bonding case. This is of a higher energy, and it takes the system a certain amount of energy to excite the electron from the bonding to the anti-bonding orbital. Okay. Now, that's the basic difference between bonding and non-bonding orbital. Well, anti-bonding orbital, sorry, not non-bonding orbital. Non-bonding orbitals are orbitals which are not obviously involved in any of these. And you can imagine the remaining orbitals, like the p orbitals and the d orbitals of the two atoms, which do not take part in any of the bonding, as the orbitals in which the electrons are there. They do not participate. And there is a much clearer, probably more focused definition on the non-bonding orbital when I discuss the bonding in a diatomic molecule and a triatomic molecule later. But what I discussed with you is the bonding and the anti-bonding orbital. The last, there's a question from Shanta Das. It says, you have discussed probability from density of the simple harmonic oscillator wave function. Can you repeat again for large state, I mean when reaching to a classical limit? Okay. Yeah, I'll repeat that, but probably put the pictures more clearly. If you recall the harmonic oscillator, and let's draw the axis, okay, and say draw the zero somewhere here in the middle, okay. So this is the potential energy, okay, half kx squared. This is a classical model. This is the x, positive x, the minus x, and the potential energy is parabolic, okay? Something like that. A classical harmonic oscillator is for any given total energy. Suppose this is the total energy for the harmonic oscillator, E1. Suppose there is another total energy for the harmonic oscillator, E2. We will discuss these two cases separately. Okay? So first, let us do the case of E1. A classical harmonic oscillator will be oscillating only between these two extremes. Okay? And when it reaches the zero, it is the fastest moving species. Therefore, at this point, all its energy is kinetic energy. There's no potential energy, zero, because potential energy is zero. Therefore, the classical oscillator swings very fast and then swings very fast again, but it stops here for a longer period of time than it stops here. Therefore, the probability of locating the harmonic oscillator towards the end is very high compared to locating the harmonic oscillator in the middle, because it's extremely fast. All its energy is kinetic energy. Therefore, its velocity is maximum. Therefore, the time it spends at that point is very minimal. Given that the velocities are 0 here and the velocity here is middle, it's easy to recognize that the oscillator spends more time in these 2 points or at these 2 points than it spends here. Now, is it any different if the energy were like this or if the energy were like this? No. Here also, if the energy is this E, the oscillator spends more time here than it spends here in the middle. The oscillator spends more time here than it spends in the middle. Now, as the energy increases, of course, the frequency of the oscillator is more. Okay? If it is a fundamental frequency, then the oscillator has it. But then since the energy is, the speed of the oscillator keeps changing. But the time it spends towards the extreme and the probability of locating the oscillator in the extreme is always more than the probability of finding the oscillator right where its potential energy is minimum. This is classical. In quantum mechanics, we don't have such a picture. In quantum mechanics, all we have is, suppose we are given a total energy E. This graph doesn't even exist. Okay? That is, you cannot draw the potential energy of a quantum mechanical oscillator exactly. You cannot do that. Because the potential energy cannot be defined exactly for each point for a quantum oscillator. It can only be defined exactly for a classical oscillator. So for a quantum mechanical oscillator, if the energy is this value, all that you know, if it is in the ground state, its wave function is going to be that. But you see, but it never reaches 0. And if you plot this as psi square x, you see that the probability of finding the oscillator in some region here or some region here, way outside of what you would have imagined the classical probability to be, something like this, okay, is everywhere. The probability of psi x square dx is for any large x is never 0. Does that mean that if the potential energy is that and this is the total energy, does that mean if this is the point where the oscillator can actually be located? You remember the classical expression for the potential energy will correspond to this value, because that's the x value, correspond to this value. But the oscillator energy is only this much. If the potential energy of the oscillator is so high, then obviously its kinetic energy should be negative. That argument doesn't work because we do not know what the classical harmonic oscillator potential energy is. We only know that it has a total energy E. Therefore, the difference between classical and harmonic and quantum mechanical oscillator is very striking in the lower quantum numbers. What happens if we do for very high quantum numbers as you ask for? Let me draw that. If the quantum number is very high, say for example, n is something like 1000, okay, what you would see is, you would see many oscillations, the oscillations each of which would be larger and larger in size, because as you increase the x raised to whatever it is. So finally you will have a very large and then you will have very close to 0. The same thing will happen on this side. So I have to draw the exact mirror of this. Of course, you assume you know what I mean. Okay, it's exactly the same thing. It's very large. Therefore, the probability of finding the oscillator towards the end, the last node, 1000 means there will be a 999th node and there will be a 1000th part. This probability is more than the probability of locating the oscillator anywhere in between this area, in between this part, or in between this part, any. Therefore, if you really plot it for very large values of n, you can't even see these oscillations anymore. And you will see that the psi square probability for very large value of n will be something like the last one, and all you would see is a sort of a continuous curve coming down to that. Okay, both these parts will be identical. Okay, so let me draw this carefully. Will be coming down to something like this and that. Okay. What it means is that now the probability of locating the oscillators at the extremes, if you draw the potential energy, it will be almost like the potential energy similar to that, which this is the maximum. Therefore, the classical probability and the quantum probability become very close to each other. And as the oscillator energy increases to very large values, the oscillator does not have to be represented as a quantum mechanical quantity, but almost like a classical oscillator. Therefore, very large values, the probability is maximum at the extremes. Okay. Yeah, okay, so that's the question which I have. Does it make any sense? So let me know. So let me go back to the beginning when I was talking about the chemical bonding part. Go back to the first part of it. Yeah, go to the beginning. Yeah, just do that. Okay. This is shared already, right? Yeah, this is already shared. So if you recall that the electron correlation problem and the description of the chemical bond using the atomic orbitals of the individual atoms is limited in a sense that it is an approximate model. If you have to have an exact solution and a very precise state for the molecular bond, you need to include all the atomic orbitals or all what is called the basis functions of each of the atom. And there are two ways of doing it. The method which I would describe in the next 3-4 classes would be what is called the one electron model or the Hartree-Fock model. In a qualitative way, I will explain that in the lectures which are coming up. Essentially, what you think is that the electrons are, to a starting approximation, the electrons don't interact with each other. Therefore, an n electron system, like a, say, lithium atom in which there are 3 electrons, or a fluorine atom in which there are 9 electrons. It is a 9 one-electron system. And each electron is described exactly by the wave function, which is exactly the same as any other electron. Of course, we know that that's not true, because the electrons do not see each other. They interact with each other. Electronic clouds interact with each other. But to start with, you have to use the approximation and then build the electron interactions through the potential energy of one electron due to all the other electrons. All that you do is you modify a single electron wave function by calculating the potential energy again. And you keep repeating this exercise until you get a reasonably good one electron model. And then the n electron system is n one electron system products. Then the Pauli's principle is important, that the electrons are identical particles. Therefore, the wave function of the n electron system, which is the product of n one electron wave functions, have to follow certain symmetry laws. Okay? Those symmetry principles and the very fact of forming these electrons and the wave functions, I will describe that in the next 3 or 4 weeks before the closure of this course. Okay? So chemical bonding is the most important reason why chemists are interested in quantum mechanics. There is no other way to describe the bonding characteristics except through qualitative arguments like what Lewis did, and then you find exceptions to the qualitative arguments. Then you have to modify it. Then you have to give approximate theories. But having seen quantum mechanics successfully explain all the microscopic atoms and all the microscopic systems, a lot of chemists actually applied quantum mechanics very successfully to study the chemical bonding properties. And I think I have given probably one lecture on the history of quantum chemistry through a write-up, which is there probably in your website. And if it is not there, I will add up. It's about 20, 25 pages, which tells you the evolution of the chemical methods and the bonding methods as the quantum mechanics was discovered around 1920s and so on. Okay, let me see if there is one more question. Sure, okay, he has done that. So he has followed that, okay? Yeah, there are other things which are interesting to the whole of quantum chemistry. Yes, here is one more, okay? Can you discuss again angular and radial nodes in the hydrogen atom radial solution, okay? Angular nodes come into the radial solution. So let me just describe. Yeah. What about the radial nodes first in hydrogen atom? You recall the hydrogen atom wave function is written by assigning 3 quantum numbers to the wave function n, l, m, and it is the radial function depends on 2 quantum numbers n and l, and the angular function depends on 2 quantum numbers l and m. Now, the radial node is a point where the RNL function goes to 0. The angular node is a point where the y, l, and theta phi, in the way we have described, goes to 0. Okay? That is real Cartesian notations. We use x, y, x, z, y, z, x squared minus y squared, for example, x, y, z, all these things. In this form of representing the real and spherical harmonics, the imaginary parts of spherical harmonics, these functions go to 0 for specific values of theta and phi, and those are called the angular nodes. When these go to 0 for specific theta and phi. Now, let's look at the radial nodes first. Okay? In the case of 1s electron, the wave function is e to the minus r by e naught, the radial function. And this never goes to 0 except when r goes to infinity. Therefore, the 1s electron has no radial nodes. There is no angular function because the only angular function that you have is 1 by root 4 pi, which is due to y 0, 0, theta phi. Okay? There's no angular node. The whole thing is spherically symmetric. Therefore, no angular nodes for 1s. What about 2s? The radial function looks like it is r minus some constant times e to the minus r by a naught. Okay? Let me find out exactly what that is. Just a second. Okay? I'll give you the precise form of that. The radial functions, if I recall in the text file that I sent you, there is an atom wave functions. So let me give you the form of the radial function as it looks like. Yeah, I'm going to do that. Yeah. Yeah, anyway, can you open this file from, it seems to be the PDF seems to be a problem, so let me open up the doc file. It's okay. I think it should be all right. This should be fine. That's a good question, the radial and angular nodes, to get back to the elementary things. But elementary things are not always elementary. Okay, so I have this. So the radial function for the 1s electron looks like 1 minus 2s electron. 1 minus r by 2a naught times e to the minus r by 2a naught. Okay. So you see that this function, if you multiply, or even this function itself, has a 0 when r is 2a naught. Okay. So imagine the nucleus. This is a naught, the Bohr radius. This is 2a naught. 2a naught. Now, along this spherical surface, everywhere, if you imagine a spherical surface, exactly at 2a naught, the radial part makes the function go to 0. Therefore, that function is 0 at all points on the surface. That's called a radial node. There is no angular node for this because this is an S function. L is 0. Therefore, there is only one node. Okay? So if you do the same thing for 3s, if you look at 3s, it is 3, 0, 0. You will see the polynomial 1 minus 2 r by 3a naught plus 2 by 3 r by 3a naught whole square e to the minus r by 3a naught. Okay. Now you see this is quadratic. Therefore, it has two solutions for which the quadratic goes to 0. Those two values are essentially, if I have to draw this, central. One value of r is some r, which is spherical, for which the radial function is 0. There is another value of r for which also the function is, the radial function is 0. So you have two spherical surfaces at which the radial function goes to 0, which means that it has two nodes, the radial. And you can now see the general part of the s orbital. The total number of radial nodes is n minus 1. The total number of angular nodes is 0. Okay. There is no angular part in the s node. What about the p orbital? Yeah. No, it's the same question. I'm just answering both these questions together. Yeah. What about the p orbital? If you think about the p orbital, let us take the 2p orbital. The 2p orbital has this radial function r e to the minus r by 2a naught. Okay. And then it's either cos theta or sin theta e to the plus or minus I phi. So there are three functions. All of them have the same characteristic. Please remember, r equal to 0 and r equal to infinity are not the nodal parts. R is 0 is a nucleus. Okay? R equal to infinity is, of course, all wave functions go to 0. That's not considered a node. The node is for finite values of r between 0 and infinity. There is no radial node. The radial function is never 0 except in the beginning, except at the nucleus, and except at infinity. However, this function does go to 0 if you take the angular part, cos theta, because if you recall the cos theta part in polar coordinates and spherical coordinates, you have this plus and minus right here, but theta is equal to 90 degrees. Okay? Therefore, in any spherical shell, if you think about it, right at the middle, at theta is equal to 90, the electron wave function goes to 0. So this is called an angular node because it depends only on the angle theta is equal to 120. It's only along the 90 degrees. In the other case, if it is sine theta e to the plus or minus I phi, sine theta never goes to 0 in an angular part between 0 and 180. Therefore, there is no contribution to a 0 due to sine theta. However, you remember we always picture the p orbitals as p plus x and py. The moment we have the representation x and y, it is either cos phi or it is sine phi. The phi value is 0 to 2 pi, the entire spherical volume. Therefore, cos phi goes to 0 at phi is equal to pi by 2, but the pi by 2 line is also the 3 pi by 2 line. Okay? If you think about phi going to 0 in spherical form, pi by 2 will be along the plane in the plane perpendicular to the z-axis. The pi by 2 and the 3 pi by 2 lines are the same. Therefore, there is one node at pi by 2. Cos theta is equal to 0. Cos phi is equal to 0. Likewise, for sine phi, the 0 and pi between 0 and 2 pi. 0 and pi, they coincide. If they coincide, there is one node, namely at 0 degrees of phi value. That is the x-axis. That is for the y orbital. The x orbital has the y-axis as the node. There's only one node for the n equal to 2 orbital because there is no radial node for 2p. So the total number of nodes is still 1. The radial node is 0, angular node is 1. Now, you see this in a similar way for the d orbital. You will see that the s orbital has 2 nodes, I've already pointed out. The p orbital will contain one r value for which the function will go to 0, and the d orbital will contain 2 angular nodes. Therefore, the moment you go to the n equal to 3, the 3d orbital, the radial part will not have any r equal to 0. Any point r at which the function goes to 0. Only angular nodes will be there. So you can see that the progression of the radial nodes and the angular nodes will be this way, that if you start from, let me write this down. So if you write down the radial nodes and the angular nodes, n, 1, s orbital, 0, 0, 2, s orbital, 1 radial node, 0 angular node, 3, s orbital, 2 radial nodes, because 2 values of r for which the function goes to 0, there is no angular part, it's 0. But what about 3p? The r function for the radial part will have only one r for which it is 0. Exclude r equal to 0 and r equal to infinity. Do not include. So these are basically boundary conditions. And there will be either p orbital is either cos theta or cos phi or sin phi, that is one angular nodes. And 3d, the radial function will contain only r square e to the minus r by 3a naught. Doesn't go to 0 for any value between 0 and infinity. Therefore, there is no radial node or 2 angular nodes. So generally, this formula turns out to be n minus l minus 1 radial nodes and L angular nodes. And therefore, people have a tendency to visualize and add these two things together. The total number of the locations in the three-dimensional plane or the spherical surface, the total number of places where the function will go to 0 is n minus 1 such values, of which n minus l minus 1 will correspond to r values and L will correspond to the theta values. Therefore, the sum of the two is the n minus 1. This is how one visualizes the radial and angular nodes. Okay, I think I have answered that question. Yeah. So I think it is now 11 and the clock is ticking. It looks like there may be other recordings and other groups to be involved. And really, I see that the 3 or 4 of you are following this pretty closely. Do the best of what you can. And if you need any help, also please feel free to write both in the discussion forum and also send the questions to me on the email. We will have 1 or 2 more such interactions, live interactions between now and the closure of the course in the next 5 weeks, I guess, isn't it? Yeah, this is 7 weeks are over now. The 8th week is starting. We have up to 12 weeks. I'll try as much as possible to interact with you live. But yes, please do tell your friends also to come in and open up with questions if they need specific answers. And live sessions are very useful for you to ask a question and get an immediate answer. If whether it's convincing or not is something that you have to go back and see it. But point is, there will be a response to your questions immediately. And please make use of this facility from NPTEL, okay? We will meet again maybe in a week or 2 from now. Until then, thank you so much, and continue to study. All the best to all of you. No, yes, thank you.